This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Let's try the reverse procedure and convert from a Y to an equivalent delta configuration. Here's a 3-terminal Y configured circuit featuring R1 with a resistance of 24.1 ohms attached to node A, R2 with a resistance of 22.6 ohms attached to node B, and R3 with a resistance of 27 ohms attached to node C. The observant among you will realize that this is the Y configuration we just solved for from our previous illustrated example problem. If everything I've been telling you is true, our Y to delta conversion should return us to the original delta configuration. That's the point. An equivalency between these two 3-terminal networks allows us to substitute one for another and vice versa. Ideally, any circuit attached to these 3 nodes would be none the wiser to the substitution. To solve for delta resistance RAB, take the summation of all possible products of the Y resistance taken 2 at a time. R1 times R2 plus R2 times R3 plus R3 times R1 divided by the opposite Y resistance, in this case R3. Our formula suggests RAB is 67 ohms. You will note that each Y to delta conversion necessitates the use of the same numerator, the summation of all possible products of the Y resistances taken 2 at a time, R1 times R2 plus R2 times R3 plus R3 times R1. If you want to save yourself some time, don't recalculate this numerator, just reuse it. To solve for delta resistance RBC, take the previously calculated numerator divided by the opposite Y resistance, in this case R1. Our formula suggests RBC is 75 ohms. Finally, to solve for delta resistance RCA, take the previously calculated numerator and divide it by the opposite Y resistance, in this case R2. Our formula suggests that RCA is 80 ohms. Our equivalent delta configuration features RAB with a resistance of 67 ohms between nodes A and B, RBC with a resistance of 75 ohms between nodes B and C, and finally RCA with a resistance of 80 ohms between nodes C and A. Ideally, one should be able to exchange our previous Y configuration with this new delta configuration, and the circuit, source, or sources attached to these 3 nodes would be none the wiser to the substitution. Additionally, you should be extremely satisfied that this second conversion from a Y to a delta returned us to the original delta configuration we started with. I've got a reasonable degree of confidence our answers are correct, and we can move on to the next illustrated example. Let's put your understanding of delta and Y conversions to the test with this set of illustrated example problems. By all means, pause the lecture and take your best shot at converting these 2 3-terminal configurations to their other-world equivalents. If you're given a delta configuration, convert it into an equivalent Y, and if you're given a Y configuration, convert it into an equivalent delta. You'll note that I've not identified the resistance elements nor assigned external nodes for these different configurations. That's your job. As long as you stay organized and consistent, your results should match mine despite different initial assignments. This being said, identifying errors might be hard in a free-for-all, and as such, let's say the top left node is A, the middle right node is B, and the lower node is C. You'll note the second illustrated example features 3 identical elements. You should notice something interesting about the resultant conversion. If you're tracking, you should have obtained the following results. Our first illustrated example features a delta configuration of 3 resistance elements, or we're being asked to convert it into an equivalent Y configuration. To solve for Y resistance R1, we'd multiply the 2 delta resistance elements connected to node A. This would be RAB and RCA. Then we would divide this by the sum of all delta resistances, RAB plus RBC plus RCA. Our formula suggests that R1 is 101.3 ohms directly attached to node A. To solve for Y resistance R2, we would multiply the 2 delta resistance elements connected to node B, in this case RBC times RAB. Then we would divide this by the sum of all delta resistances, RAB plus RBC plus RCA. Our formula suggests that R2 is 57.7 ohms directly attached to node B. Finally, to solve for Y resistance R3, we would multiply the 2 delta resistance elements connected to node C. This would be RCA and RBC. Then we would divide this by the previously calculated sum of all delta resistances, RAB plus RBC plus RCA. Our formula suggests R3 is 72.2 ohms directly attached to node C. Our equivalent Y configuration features R1, a 101.3 ohm resistor directly attached to node A, R2, a 57.7 ohm resistor, directly attached to node B, and finally R3, a 72.2 ohm resistor, directly attached to node C. Ideally, one should be able to exchange our previous delta configuration with this new equivalent Y configuration, and the circuit, source, or sources attached to these three nodes will be none the wiser to the substitution. Our second illustrated example features a Y configuration of three identical resistance elements, and we're being asked to convert it to an equivalent delta configuration. This is what is known as a balanced network, and that all legs of the Y are identical. Ideally, the resistance elements in our equivalent delta configuration should also be identical and balanced. Application of the Y to delta conversion formula for our first delta resistance RAB yields an interesting result. Delta resistance RAB is the sum of the products of the Y resistances taken two at a time, divided by the resistance opposite of it. Our formula suggests RAB is 360 ohms, as does RBC and RCA. Note, because every resistance element in the original balanced Y configuration is identical, a simplification I'm calling RY, the delta conversion calculation for any delta resistance can be simplified as 3 times RY. This similarly suggests that when presented with a balanced delta configuration, the equivalent Y resistance is 1/3 the delta resistance. Either formula yields the following results. Our equivalent delta configuration features RAB, a resistance of 360 ohms between nodes A and B, RBC, also a resistance of 360 ohms between nodes B and C, and RCA, also a resistance of 360 ohms between nodes C and A. Ideally, one should be able to exchange our previous balanced Y configuration with this new balanced delta configuration, and the circuit, source, or sources attached to these three nodes will be none the wiser to the substitution. In summary, resistance elements for an equivalent balanced Y configuration are 1/3 the magnitude of resistance elements in a balanced delta configuration. Conversely, resistance elements for a balanced delta configuration are 3 times the magnitude of resistance elements in a balanced Y configuration. These make great shortcuts when presented with balanced networks. Alright, that's about it for delta Y conversions featuring resistive elements. In conclusion, this lecture presented a means of converting between two different 3-terminal resistive networks known as delta and Y configurations. Later lectures will make use of this technique to simplify complex circuits. Delta Y conversion allows a degree of flexibility in circuit analysis scenarios, and establishing an equivalency between the two configurations allows one to escape seemingly inescapable circuit analysis traps. Remember to review this material and practice these techniques as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about these resources, and be sure to check out the Big Bad Tech channel for additional resources and updates.